Welcome. In this video we will work out an exercise about a galvanic cell together. Let's have a look at the reaction that we will discuss. Solid aluminium and cobalt ions will react to form aluminium ions and solid cobalt. Now we are going to determine the half reactions. In this case, these are the half reactions. Oxidation of aluminium from 0 to 3+ and reduction of cobalt 2+ to cobalt 0, with potentials of -1.66 volt and -0.28 volt. For the drawing of the galvanic cell, it is handy to know which half reaction occurs on the anode side and which one at the cathode side. Aluminium is the reductant because it loses electrons, so it will be on the anode side. Cobalt is the oxidant because it gains electrons. To have a better look at what is happening in the galvanic cell, we will start with two beakers. Then we put in our electrodes of aluminium and cobalt and the wire. We will have an electrolytic solution of the metal ion and sulfate as the counter ion in each beaker. We already determined which side was the anode and which was the cathode, so let's show it here. From this, we also know the positive and the negative pole. Since the electrons move from the negative to the positive pole, we know the electron flow is clockwise. We only miss one thing at the moment, the salt bridge. We need the salt bridge so the charges are balanced in the solutions. Otherwise, there cannot be a current. Now, let's look at the cell potential and if the reaction is spontaneous. First, remember the formula for the standard cell potential. You can calculate the standard cell potential by subtracting the anode standard potential from the cathode standard potential. This gives -0.28 volts plus 1.66 volts, since the double minuses become a plus and the standard cell potential will be 1.38 volts. Now consider if the reaction is spontaneous. Do you remember the criteria? The cell potential should be higher than 0.3 volts, which it is in this case. The reaction occurs spontaneously. Next, we will calculate the electromotive force. The formula to calculate the EMF is given here. We will need the reaction conditions and concentrations at the anode and the cathode for this formula. Keep in mind that we need to put the ratio of reaction in the power of the concentrations because we are looking at the equilibrium constant. The temperature is 200 degrees Celsius and the concentration of the cathode is 375 millimoles per liter and at the anode 50 millimoles per liter. Next, we already know the gas constant and the Faraday constant, and we can get the N from the reactions since there are 6 electrons transported. Let's fill in the formula with all the values given. Note that joule per coulomb is the same as volt, that it is rewritten here. Therefore, for these reaction conditions, the EMF is 1.312 volts. Now, we will look at the last topic. You learned in this unit the change in Gibbs free energy. The following formula you know for Gibbs free energy in galvanic cells. For this, we need the Faraday constant, the amount of electrons transferred, and the EMF, which we just calculated. Filling this in gives a Gibbs free energy of -760 kilojoules. Thanks for watching, and we hope you found this video helpful in understanding how to work out an exercise on a galvanic cell.